Hey there, TouchDesigner developers. Welcome to another TouchDesigner tutorial. In this video, we are going to look at recreating a spirograph in TouchDesigner. For those of you who are not familiar with the spirograph, it was a children's toy marketed first in the 1960s, which used a series of interlocking plastic gears, which you could use with a ballpoint pen to start drawing these kind of amazingly complex geometric drawings with. Interestingly, behind what could be seen as a simple children's toy, there's actually some complex math going on. And fortunately for us, these formulas are very widely documented, and so we can take those and actually use them within Touch to recreate a similar kind of drawing program. So what we're going to do is we're going to build a program that allows us to draw these spirograph patterns and be able to play and pause the drawing, and also reset our drawing so that we can start fresh. There are a variety of parameters that we can modify to get an almost infinite amount of drawings out of this function. And this one that you're seeing on the screen now has actually been drawing for quite a while. Just to give you an idea of how long it might take for something like this to draw, I'll reset it now and show you what happens when we first start drawing. So from there, I guess we can jump right into looking at the network, and then we will start to build it. So we actually use a chop execute dat, like in some of the previous tutorials on this channel, to apply those mathematic functions. And so we have a small chop network that's connected to, and then we're taking that chop information and running it into a small SOP network, which is using the limit SOP to create a very small line which moves around the screen based on that chop info. From there, we render that information to tops, and then we use a feedback loop to allow this drawing to accumulate on the screen. So like our other tutorials, I will start by deleting this, but before I do, one thing that I wanted to note is that our code here in the end is essentially only 2 lines. It's pretty simple. You are able to recreate this kind of functionality in chops, but just for those of us who haven't dealt with the chops versus code discussion yet, this is how complex your chop network would have to be in order to recreate that same functionality that we built there with just 2 simple lines of code. You'd need all of this to get that exact same functionality. I just worked with this initially to see if it was possible to get that kind of output via chops and how complicated it might be, but since the chop execute method with Python code is so much easier, we're just going to look at that method in this tutorial. So I'm going to start, as I said, by deleting everything, and then we will start to build our network. So all of the math behind this is pretty widely documented, but the specific reference that I was using to create this comes from David Little, who is either still is or was working at the mathematics department of Penn State. He posted this reference a long time ago in the early 2000s, and it's still just as useful today for us. We're going to use these 2 equations that he's got posted here. In mathematic terms, what is actually going on within a spirograph is called an epicycloid. And if you look up this term epicycloid, or even spirograph on Wikipedia or other sites, you can get the actual mathematic foundation behind this phenomenon. And it's very interesting. It has to do with rotations based on circles and radii and positioning. But we're not really going to get into why this sort of functionality works in terms of math. We're just going to apply it to TouchDesigner. So we're going to take these 2 formulas and work with those within our chop execute dat. If we want to understand what the variables within these formulas mean, if you click this link at the bottom of the page, I've kind of zoomed in on here so it won't look like this necessarily on your machine. If you click View Original Version of Spirograph, it'll take you up to an even older version of the page from the late 90s, which has definitions for each one of the variables within this function. So we're essentially going to be setting up a constant for 2 different radius parameters and then a position parameter. And we're going to set those up via some chop channels. And then the other part of the function that's important to understand is this t parameter, which is normally standing for time. And in terms of our TouchDesigner sketch, that is basically what allows us to change the speed at which the drawing is being created. So we don't really want to attach that to a kind of fixed time parameter like ABS time.seconds that has a very specific rate at which it's increasing that we don't really have control over. We want to have something that we can modify the speed of this drawing with, and we can actually create a stand-in for time here with speed chop, and we'll look at that now. That's going to be the first part of our chop network that we create. So assuming that you've got your blank network ready to go, we can start by dropping down a constant chop, and then from there a speed chop. Remember that when you enter a constant value into a speed chop, like 1, it will just increase indefinitely. It'll just count upwards infinitely for us. So we can use this to, again, stand in for time in our function and allow us to plot those curves on the screen. Remember too that if you modify the constant chop's value of that chop channel to say 0.5, it actually changes the rate at which the speed is increasing. So that is how we're going to be able to vary the speed at which our drawing is being made. So one other thing that's nice to have the ability to do, as I mentioned in the intro of this video, is be able to play and pause the drawing of our spirograph, and that can be useful if you hit a certain point in your drawing that you really like and want to capture something like that. It's a great function to have, and it's really easy to create. So if you drop down a keyboard in chop, we're going to use the 1 key on the keyboard to be able to play and pause the increasing of this speed chop. We're going to do this via a logic chop. So if we use the logic chop, drop 1 down, and then within the channel preoperator parameter, change it to toggle, what will happen is if we hit the 1 key, it will toggle that chop channel on and off. And then if we take that and first attach a null to the end, in case we want to do any further modifications, and then we use a math chop to combine this chop channel with our constant chop, we can essentially create a switch which will turn the sending of this constant value into our speed chop on and off. And from there, that will actually pause the increasing of that speed chop. So we're just going to right click on that and add a math chop, and then we'll connect this null to the math chop, and then within the math chop we will combine these chops via the multiply setting. So again, within combine chops, open the drop down and hit multiply, and then you'll see that our speed chop has stopped counting upwards, and if we hit the 1 key and toggle that chop channel on, it'll start increasing again, and that is what enables us to start and stop our drawing. I'm going to connect a null to the end here, and then in between those parameters, I'm going to rename this chop channel from channel 1 to something else. Since this is standing in for t in our equation, I'm going to rename the chop channel to t, just so that we're clear that that's what's going on. So within your rename chop, just put t in the 2 parameter, and then at the end here, I'm going to change this to say speed null for the title of that null, just so I'm clear that that is what that chop is supposed to be doing. So as I was mentioning before, within this equation we have a series of constants, these radius values and this position value. And we want to be able to set those variables, but also it'd be nice to be able to modify them, because that is what gives us that kind of infinite variety of output from our spirograph system. So instead of just using a constant chop and having those values set for us, I'm going to instead use slider comps, because it'll just make it easier to interact with and be able to adjust things on the fly. You could use like a MIDI controller or something else if you want to. I've experimented with that and it's also super useful, but not everyone has access to a MIDI controller, so we're just going to use these sliders instead. We're going to name these slider comps based on the parameter that they're modifying. So I'm going to grab the titles here, radius 1, radius 2, and position, and add those before the slider name so that we know exactly what we are modifying. So this is radius 1. I'll do radius 1 underscore slider, get rid of that number at the end, then radius 2 underscore slider, and then finally position space slider. Okay, so now those are telling us exactly what they are modifying. One thing that we're going to want to do before we continue is that the way that a slider comp works is by default it will display in the background of your, or within the output of your top network, because they're meant to be used as a sort of user interface element. And in the case of this program, I don't want those to display on the screen because I just want to see the output of my spirograph, and then we'll be able to edit the parameters. Instead of creating the interface on screen, we'll be able to edit those parameters within our network editor window like we are now. So to disable that displaying of those on the final top output, we have to come to the panel page within our parameter window and turn this display setting to off, and then they will not display within that top network that we eventually create. From there, I'm going to merge all of these chops into a single chop. Slider comps have a chop output, which is how we actually can use that slider to modify different parameters. So I'm going to connect all of these to that merge. And then because the channel names are not really, they're pretty ambiguous right now and don't reference what's going on here, I'm going to use a rename chop to rename those chop channels to something else. So I'm going to use, again, those names from this page. I'm going to link both this page and the previous one that I was on in the description of the YouTube video. If I haven't already mentioned that, they will be there for you to look at, and to give credit to David Little for producing this content. Instead of using the upper and lowercase r, just because they're so similar to each other, I'm going to use the radius 1, radius 2, and position names for those chop channels, just for clarity's sake. So if we go back to touch, within our rename chop, I'm going to type in radius 1 space radius 2 space position. And now those chop channels should have the correct names. I'm going to add a null to the end, and then I'm going to change the name of this null to constant space null, because these are the constants within our equation, and I want to clearly know what that null contains. That's actually it for this initial chop part of the network, and what we're going to do now is work with the chop execute dat to write a little bit of code, and then from there we'll move on to the more advanced parts of the network. So go ahead and drop down a chop execute dat, and for this example, instead of opening up the viewer here and editing our code this way, I'm actually going to open up an external text editor because I want you guys to actually be able to see what I'm writing instead of just having very small text on the screen. Before we do that, however, I want to make sure that I'm referencing the correct chop that I want to have this chop execute run its Python code based on, and that in this case is going to be the speed null chop that we've set up, because we want to use that the time function is what's going to essentially run our code here. So if you drag that speed null on top of the chop execute dat, it will automatically make that reference, and you should see within the chop section here speed null. And then before we get going, we're just leaving it in the default value change setting, which again is saying that we're only going to be using the onValueChange function definition within that chop execute. So on my machine, I have VS Codium set up for editing code, and so when I hit Command E, it will open that text editor for me. On your machine, if you don't have a text editor or a code editor or anything like that, you can either hit the Viewer Active button at the bottom right and edit the text via that operator, or you can right click and hit View, and then it will give you an external window which you can then edit the code within. However, I'm just going to do VS Codium because it's easier for you guys to see. So the first thing that I want to do before we're going to be writing almost exactly this equation that we see on this website here, but we want to be able to reference these constants that we set up up here in our network. And we're going to do that at the top portion of this chop execute code. So I'm going to come over to this null just so we can make sure that we've correctly referenced our channel names, and then we'll make those references at the top. I'm actually going to use, in this case, I'm going to set them equal to the actual names that they use within this function so that we can just copy it exactly as we see here. And it should be legible enough for us now. So I'm going to start by setting that radius1 value, and I need to do a reference to the specific chop channel within this constant null. So I'm going to start by typing in operator, op, open, and within my text editor automatically adds a close parenthesis. Make sure that you also do the same if you're not using one. Single quotes, again, make sure you have a closing second quote on the end. And then the operator's name that we're looking for is constant underscore null. And then we need to reference the specific chop channel that we're looking for. So use the brackets, make sure you have opening and closing ones, and then we need the specific chop channel called radius1. And that has completed that variable assignment. The second one, if we remember from our formula, is lowercase r, which is radius2. So if I just open everything back up, I'm actually just going to copy and paste this line of code so that we can just slightly modify it to get that variable assignment happening. So lowercase r is equal to the radius2 chop channel. And then finally, p, which is for the position. I guess I could have pasted that. We'll set the final one to p, and then we want that referencing the position chop channel. So we've set all that up, and now we can actually write our equation, and those different variables that we saw here now have something they're actually referencing, and so it'll work. Before we continue though, we need a place to actually assign these final x and y values to. And that's going to be eventually the thing that allows us to drive the movement of our geometry on screen. And so what I'm going to do is set up another constant chop at the end or after this chop execute dat. I'm going to set up two channels, one for the x position, which I'm just going to call xPOS, and then one for the y position. And then from there we can actually reference those specific parameters of this constant and set them to those y and x, or x and y position outputs from that function we're going to be using. I'm going to change the title of this to position underscore constant, just so that I know that that is what this constant is doing. So now we can actually start to write this equation out. Basically what we're going to be doing is the left side of the equation is going to reference that constant chop that we just made, and then the right side is going to look pretty close to what you see on the screen here. The only difference is that we won't have this t variable. Instead, we're going to be using the input to that chop execute, which is coming from that speed null chop, but we'll look at that in a second. So let me just bring this TouchDesigner window back up and then open up this. Okay. So to start, we need to, as I said, we need to reference that constant chop that we just set up, and we need to reference the parameter that sets that constant chop channel for the X position and the Y position channels. So remember that you can, within the parameter window, click on the title here and get a drop down which tells you the parameter's referenceable name, or you can just mouse over it and you'll see both the names on the left are exactly the same in that dialog that pops up as the ones you see here. I'm just going to leave these open so that I don't have to have my mouse over that to see what the referenceable parameter name is. And then we're going to create those parameter references within our onValueChange function definition. So we need the operator's name first of all, which is position underscore constant. And then we're not referencing a chop channel, but rather a parameter this time. So we need to type in .par to say we're looking for a parameter, and then the name of that first parameter that we're going to want to modify for the X position is called value0. So we can type in value0, and that will complete that reference to that parameter. Now we can actually write the equation that will provide us with our X position. So since we've set up our constants already and that's all good to go, we can basically write it as we saw it on that website. And we're going to start by creating this first section here where we're adding our R values together and then multiplying them by the cosine of our time value. So since we use the same variables that we saw on screen, we can do R, capital R plus lowercase r, and then we need to multiply that by the cosine of our time value. If you just type in cosine, it will not work. You might think that's possible, but you need to reference the math library within Python, and so you have to do math.cosine in order for the cosine function to work. And then our time value, again, remember, is not t in this situation. It's actually the input to this chop execute dat, and we can reference the current value of the input to our chop execute via this val input to this function. So we can just put val within that, the parentheses for that cosine function, and that will give us the time speed value that we set up in our chop network. We're going to continue by adding p times math.cosine, and the cosine is for the X positioning. And then if we look at our function, we need to have our radius 1 plus radius 2 within parentheses so that it follows the order of operations correctly, and then we're going to multiply that by our time divided by radius 2. So let's come back here and we can follow that pretty much exactly. We're going to want to do within, remember, within a second set of parentheses, we want to make sure that that radius 1 plus radius 2 is isolated within those parentheses so that it follows the order of operations, and then we're going to multiply that by our time value divided by the radius 2. So val over lowercase r. And that actually has completed that function and the assignment of that value to our position constant. You could add a second set of parentheses that encapsulate this val over r part of the function, just for clarity. You don't have to, it will still function without that. You can add spaces too if that makes it easier to read. From there, we can actually copy and paste this and create the assignment and creation of our Y position value. So in this case, we're going to need to reference the value 1 parameter of our position constant so that it modifies that specific chop channel instead. So just change this value 1 parameter reference to, or value 0 parameter reference rather, to value 1. That's how this second section should read now. And then the only other thing we're going to do within that function for the Y position is change the cosine function to the sine function. And that completes our work with the chop execute that. If you're using an external chop or external code editor, make sure that you hit save so that it updates the code within TouchDesigner. You don't want to lose those changes you just made. If you're within Touch, you won't have to worry about it. It'll automatically update. And what that means, if we've written everything correctly, is that if we were to start the playback or the increasing of the speed chop again by hitting the 1 key, we should start to see position values output in this constant chop. So if I hit the 1 key now, we'll start to see those position values in that constant chop. So we can actually move on from here and start preparing that information to be used with our SOPs and start getting to the visual stuff after that. One thing that I just want to note is, again, I want to reiterate how amazing it is that we were able to recreate that entire gigantic chop network's worth of functions and math with literally just 2 lines of code within this chop execute dat. That really illustrates very clearly the advantages of being able to use a little bit of code within TouchDesigner. All right, so now that we've finished the coding portion, let's continue on by prepping this data for our SOPs. And basically what that requires us to do is add a trail chop to this in order for it to have a little bit more data for our SOPs. And I'll show you why that is once we drop down the SOPs. So make sure that you've added a trail chop, and within the trail chop I really only added a little bit of data to this. What the trail chop does is it gives you a kind of extended window of chop information over a period of time. And I literally set the window length here to 0.1. And so I just got a little bit larger of a window of time than what comes out of this constant, which is just giving us a single value. Then I drop down a null at the end, and I'm going to call this position null, just so that I know that that is where the positioning information for my SOP network is supposed to be coming from. What we're going to do is actually use this chop information to start drawing stuff with our limit SOP. And for those of you who are not familiar with the limit SOP, the definition says that it creates geometry from samples fed to it by chops. It creates geometry at every point in the sample. So you can use this to draw a variety of things. If you drop down a limit SOP and then go to the output page, you can see you have a variety of different types of output that you can get. You can get lines, you can get primitives, spheres, tubes, strips. We are going to use, in this case, the output type called strips. I just found that visually it created the most, or the best and most adjustable output that I was able to find. We will just, I guess, modify the settings here and then create the chop reference. The major changes that I made on this output page were changing the divisions to 2, and then the radius I set really small to 0.0025. And then the only thing that I turned off from there was compute normals. And that was it. And then we need to make our chop reference so that it starts actually doing something. So again, we can just drag our position null on top of it to tell it that's the chop we want to look at, and then we need to tell it which specific channels within that position null we want it to use to draw that information. So for our X channel, we're just going to set that to X position, and then from our Y channel, we're going to set that to Y position. And then what's actually happening now is it's drawing a very small little line in space using that strips output type, and we're going to add some color to that, and then we're going to use a geometry to render it, and then eventually get into the world of tops and create a feedback loop. And that is actually what's going to allow us to draw those spirograph shapes on the screen. So I approached this by adding a material SOP after, and then to enable me to add color to it. And then I dropped down a constant matte above, and I use that to add for the material of this material SOP. And then to give me a slowly or a slow color change, I dropped a noise top rather in, and use that as the color map for this constant. So what we're going to do within our noise top is actually change quite a bit of the parameters. The first thing that I did was I just wanted the texture or the line to not have a kind of noisy texture to it. I just wanted it to be like a solid color at any given point, but then for that color to change. So you don't really need a lot of information for that to work. So I came to the common page here and set my output resolution to 1 by 1. And that just gives us a single pixel of color. And then I came back to the noise parameter page and set the period to 15. And then I finally added some translation via abs-time.seconds so that it will rotate through the values within this noise. So I've typed in abs-time.seconds times 0.0025, and you'll see now it's giving us a variety of different values which change over time. I wanted it to be color and not grayscale, so I turned this monochrome switch to off. And then finally, I set the pixel format to 16-bit, just so that I could have a wider range of colors expressed by that. And then once all of those changes have been made, I drag that over top of my constant matte, and that applied the color mapping to it. Again, you can't really see what's going on here because of the way that this is automatically adaptive homing is being applied, but trust me, it will work in the when we get it into the geo and render it. So from there, I dropped down a texture SOP because this creates UV attributes, and if you don't place this down, your render top that we're going to put down later will start yelling at you. From there, I put a null down, and that actually completes the SOP portion of the network. We can continue by adding a geo, which is what we're going to use for creating the rendering of this into tops. And then I added a camera and a light so that the rendering would function correctly. I did a little bit of modification to these two, the camera and the light, in order to get the output image in frame the way that I liked. So within the camera, I just modified my Z translation to 4, which brought the camera a little bit closer to the output geometry. And then with my light, I changed the translation to 3 in the Z direction. That completes our work with the camera, light, and geo. We can now drop a render top down and start to get this information on screen. I modified the output of my render top to be 1280 by 1280 because I wanted a square instead of a rectangle. And if we display this in the background, you can see very, very faintly that we have a tiny little line moving around our screen. And this is the moment, I guess, where I can talk about what that trail chop afforded us. If we add a background so that we can hopefully see this a little bit better by just dropping a transform top for a second and then using the background color parameter. Okay, now you can see that line a little bit better. Without the trail chop, you can see that we really can't even see anything because it's drawing a single point on the screen at any given time. So the trail chop is adding more data to our chop channels by recording it basically and outputting it over a period of time instead of just at that kind of single point. So we get like a history of it within the trail chop, and that is what is adding length to our limit SOP. So if you were to increase the length of this to 1, the line that is output by the limit SOP gets longer. However, you could just keep increasing this and have something that recreates that drawing method that we saw at the beginning, but it's going to be a lot more computationally expensive than just setting up a simple feedback loop. So I found that by just keeping this window length pretty short, that we could get an output that, at least on my machine, ran reasonably well. I'm dropping frames now because I'm recording a video at the same time, but it ran pretty smoothly when I was just working with that alone. So now that we've got that set up and everything kind of explained, we can create the final feedback system and output, and we will be good to start creating those drawings. So I started off by adding a blur to this output of the render, because you won't necessarily see this if you don't drop the blur down, but you got a little bit of pixelation as these curves were being drawn, and the blur helped to kind of smooth it out a little bit and give it less of a hard-edged look. So I modified the settings within the blur quite a bit. I'm up to this filter size 21, and then I changed the sample step to 0.05 for both of the offset X and Y parameters for that. And that was it. Then I actually set up the feedback loop. So the feedback loop is really simple. It's just going to have a feedback and a blur, and that's it. And that will allow us to accumulate those drawings on screen over time, so it creates a connected line instead of just that small line that we saw on screen. So I'm going to start with the feedback top. I'm going to connect a null. I'm going to attach a composite to that, and then connect this null to the composite. I think we just used, the over operation within that composite. And then I added the blur within that feedback loop. Make sure that you're then dragging your composite on top of your feedback top so that it starts the feedback loop working and has the target top reference correctly set. And then we can't really see it, but now it's actually drawing on screen. And the blur needs to be changed so that our line doesn't get continuously more blurred out over time. So what I'm going to do is add those settings now, and I set my filter size to 2, and then the sample step really, really low to 0.002 for both. And what that did was it added a little bit of blur over time, and it started, we need to actually set up a reset to our feedback loop. It eventually allowed for it to get an almost colored pencil kind of look with a little bit of blurred out graininess to it. So I'm going to now set up a keyboard in Chop so that we can reset this feedback loop because you won't be able to clear the drawing from the screen otherwise. I'm going to use the 2 key this time. So change your keys parameter to, say, the number 2, and then we're going to add this to our, make a chop reference to the reset parameter within the feedback top. And that, if we hit the, oops, not the 1 key, but the 2 key, the 1 key, remember, is what allows us to draw in the first place. That gives us a consistently accumulating drawing system that will draw the spirograph shapes on the screen. We have a pretty boring output right now because we need to go modify some parameters, but that is basically it for the network. So to finish it up, I'm going to add a transform, which I'm going to use to add a white background in. I did white because it looks like paper. You can use black. It also looks great with black or a variety of other colors. But now we've got that composited in, and then I'm going to add a null and an out so that we can view this in perform mode. If we want to view it in perform mode correctly, we do have to make sure that our project 1 container has the correct 1280 by 1280 width and height set. So make sure that you've done that within the project 1 parameter window. Let me make sure that I didn't change anything else. Oh, one thing that I did do that I forgot about was I set within my render top here the output of the pixel format to be 16-bit, just because you'll sometimes get, if you're attenuating the signal within the feedback loop by turning down the opacity and having it kind of fade out over time, you'll get residual information left over after it fades out. So with the 16-bit format, I was able to overcome that. And as I said, we now have a system that is drawing those effects, and it looks super boring right now because we haven't modified anything within this parameter window. So you can start to use these sliders if you select them and turn the viewer active on to modify the settings that are being currently drawn. You're going to have to experiment a lot with these. There's, as I said, almost infinite variety that you can generate via these settings. I'm going to clear my screen. Every time you modify them, it will have all kinds of crazy stuff drawn on the screen, but if we clear it and start over, now we should get an output that looks very different from that previous one. And again, you'll just have to keep exploring with different settings with these sliders to get different output. So one thing that I wanted to note is that you can increase the speed at which this thing is drawing via that constant chop that we set up at the very beginning. However, the more that you increase this constant, it will basically increase the speed, and as the speed increases, it will have a harder time drawing smooth curves and basically be unable to draw smooth curves after a certain point, and you'll start to get more jagged kinds of geometry out. So that can be used as an effect, of course, but I just wanted to show you that you're not going to be able to generate the same kind of smooth curve drawing that you get with a slower rate of speed. And I think that has to do with the way that the limit stop works and the fact that the faster the data that's coming into it is changing, the harder it is for it to be able to draw or keep up with that information and smooth it out. So if I come within that constant 1 chop and start to increase the drawing speed, you'll see that like a value of 1 still gives us like pretty smooth. You can see sometimes we get a little bit of like jagged edges, and it's not quite as smooth as that 0.5 value. But then when you really start to crank it up to like 2, we start to get some flat areas, and our curves really are no longer very smooth at all. You can really see this when I reset here. You can see how the lines are no longer very smoothly curved. If we keep increasing, we can move even further into that geometric territory and get even less accurate curves. And then, you know, the higher you go, really, you can just start getting some crazy kind of very geometric output. So I just wanted to show you that that is how you would do those kinds of things, but that it's really not, at least with this method, without some maybe modifications that you guys can figure out. You really, if you want the smooth curves, you have to be drawing at that slow rate of speed. So that is it for this tutorial. I'm going to let this draw for a little while and come back and close it out just so that you can see what this particular pattern looks like after a period of 5 or 10 minutes. I really look forward to seeing what everybody else does with this technique and how you can start adapting it. I mean, this is 3D SOP geometry that we are generating here, so you could, in theory, start pushing this even further and making more complicated and amazing output with it. But I thought that this would be a great starting place for taking those mathematical functions and start applying them to get really cool visual output within Touch. So we'll jump back in here in about 10 minutes and see how this drawing looks at that point. So this is what we ended up with after 5 or so minutes of drawing. So again, just start playing around with those different parameters that we've set up with these constant values that come out of those sliders. The other thing that you can actually do is start using chops like LFOs or something else to modulate these parameters instead of just having them set to constant values, and then you'll get a drawing that evolves basically over time or like modulates between different settings, and that will give you even more complex variations on your screen. Again, as I was saying, since it's all 3D geometry, you have options of dealing with modifications to that geometry via SOPs. You could try working with instancing. You can, within your feedback loop, add different effects so that it doesn't just like draw on the screen like this. You could scale it or add opacity changes or stuff like that. There's a lot of creative opportunities because we're now within Touch instead of just dealing with this on paper. You can take this and really turn it into a digital piece of art and start modifying all kinds of different things to make that happen. So again, I hope this was helpful and useful for you guys. I think it's a really fun technique and a really good example of, number one, the benefits of using a little bit of code, how cool the output can be when you start looking at math and using that as the foundation for some of this functionality. And also like how you can start to draw lines and things like that on your screen. That was one of the things that I struggled with when I started working with Touch, and I think that this method is a pretty useful one for getting that kind of line based work output. So as you're recreating this technique on your own machine and starting to export or output the visuals that you're creating and potentially posting that to Instagram, use the hashtag #TD_Spirograph, which I've got on screen now, so that we can start to see the different types of outcomes that people are arriving at via taking this technique and adapting it. I'm really excited to see how different people take this and make modifications and create alternative versions that start with this and end up somewhere different. I really think there's a lot of opportunity for creative exploration with this technique, and I'm looking forward to seeing it all on Instagram. So again, use this hashtag that I've got on screen, #TDSpirograph, to tag your images as you post them. So with that, that concludes this tutorial. As always, like and subscribe. I will continue to be posting more and more content over time as a part of this series, Another TouchDesigner tutorial. If you want to see what I'm up to on a day-to-day basis, follow me on Instagram @JackDelora. It's the same username as this channel, and I'll be posting stuff on a more regular basis, experiments and things that I'm working out for future videos or just for fun. If you have any issues as you're implementing this technique, feel free to reach out. And if you have any requests for content that you're interested in seeing me cover, also feel free to reach out via a comment, message, or a message on Instagram. And with that, I'll sign off. I'm looking forward to seeing you in the next video.